Hey, Andrew McLaren here. Today we're going to be going over oxidization numbers and formal charge and when you use them, because it can be a little bit confusing. This video is intended for someone who's heard a little bit about both of these terms, but you're not sure about when you use them or why the formulas are similar but slightly different. And if you understand why we're using them in different situations, then you'll use the right one in the right situation, right? So we'll go over when you use them, then we'll do a couple examples so you can contrast these two things, and then we'll do some example problems where you would be asked to work with one or the other, oxidization number or formal charge. Okay? The main idea is that they're both like charges of an atom, kind of. When we're looking at oxidization numbers, you're really thinking kind of like ionically. And when you're thinking about formal charge, you're kind of thinking covalently. So, what I mean by that is electrons are split evenly when we're looking at formal charge, and they're just given to the most electronegative atom when we're doing oxidization numbers. So, this is like a little bit of an easier calculation, and it's a little bit faster. And you just kind of look at the charges that these things want, and you use that. You're like, what does the charge normally want when this forms an ion? So this is like the charge of ion, really, and this is more of about satisfying octet rules. And so you're looking more at like covalent bonds and actually looking at bonds when you're talking about formal charges. Oxidization number, typically you're just working with like a formula or something like this, whereas like a formal charge is gonna be actually something where you're drawing it out and you've got uh, some bonds going on here and you're trying to figure out what the thing looks like. So it's a matter of drawing out the structure for the formal charge. And this is typically more to do with like redox reactions when you need to identify what is being reduced or what is being oxidized. So oxidization number is basically determined by the charge the thing likes to normally take. And it's, if you think about it, like there's a ton of tables where like this is always one, this is always two, this is usually minus two, this is usually plus one. It gets kind of confusing. What I want you to do is think about this in terms of electronegativity. And so we can say that like that electronegativity, it's you're gonna have like more affinity for electrons as you get closer to fluorine, basically. This is super electronegative. It's always gonna be minus one. These also want to be minus one. The only case where they're not going to be minus one is if they're bonded with fluorine. Like if you've got like chlorine and fluorine bonded together, in that case, then you would give like the minus one charge to the fluorine, and this would be maybe plus one if the whole thing's charge is zero. So these are usually minus one. Rarely they're going to be plus one because they're working with fluorine. Oxygen is usually minus two unless it's with fluorine as well. So it's kind of interesting in that regard where if you then look at like oxygen and fluorine, if those two were bound to each other and neutrally charged, this would have to be the minus one and this would have to be the plus one. So like oxygen wants to be minus two unless it's with something that's more electronegative. And I believe that oxygen is the second most electronegative thing than fluorine. So these things, if they're bound to oxygen, will let oxygen be the minus charge and these will be the plus charges. But they both defer to fluorine. And similarly, if you go all the way over here, these guys, they give off electrons very easily. They're always going to give off one, always going to give off two. Hydrogen, because it's got two electrons, or that s orbital, can either gain an electron or lose an electron easily. So it can do both. Now it's normally going to be, because it's going to be normally combined with something that's more electronegative, they'll take the minus charge and this will become plus charge. So it's usually plus, but if you have like, the exception to this would be like if you have like lithium hydrogen or something like that. In that case, this is a more negative charge and this is going to be your more positive charge. So you can think about as these kind of like overwhelming other things in terms of charge and just kind of determining, because they're very likely to give off their electrons, they'll always give them off. Fluorine's always going to be accepting them. These things tend to accept them unless they're working with fluorine, right? So that's the main idea with oxidization number. It really has to do with electronegativity. So if you think about it kind of holistically, instead of just like a list of all these numbers, there's like, if it's this, then that's that. That is an easier way of doing oxidization number. Also, you typically see something like this when you're doing oxidization numbers, like the formula. And you can see in this example, carbon and hydrogen. Carbon's more electronegative. It's closer to the upper right than hydrogen. So this will be the minus charge, and this will be the plus charge. And I know this is gonna throw someone off somewhere. You typically don't look at the molecular structure when you're talking about oxidization rules, but if you did, this is what it would look like. So you're basically giving all of the charge to the thing that's more electronegative. So it gets all of the electrons that are in the bonds. So its charge is -4. It normally has a +4 charge. There's 0 electrons that are just free floating. And then we've got 8 electrons that are in the bonds around it, right? And so if we do that algebra, that's -4. Same thing with this oxygen. It's the same sort of thing. It normally has 6. So you've got that number that it normally has, minus the number of electrons that are freely floating, minus the ones that are in bonds. Basically, if an electron is nearby this atom, we're going to count it as like fully near that in terms of its charge or its oxidization number. And so you're just giving all of the charge. Anything that's in a bond, it's giving as much charge as in the cloud for the oxidization number. Remember, we're making an assumption. We're kind of thinking like ionically, and so we're giving all of the charge to the more electronegative thing. Again, you typically don't see things like this when you're doing oxidization numbers or redox reactions. You can also look at water though, and you can say like, oh, well, in this case, the oxygen is like, typically you'll have a problem like this and you'll have to just do the number thing. And you're like, oh, well, this is going to be -2 and I've got one of that. There's 2 of these. Each one of these needs to be +1. So they kind of cancel each other out. If you were to look at that molecular structure, you're basically saying, I'm giving the electrons in this bond to the oxygen. So the oxygen can have that -2 it's its oxidization number. And in that case, the hydrogen, it normally has 1. There's no free floating electrons here. And there's none that it's really feeling because it's giving all of that bond to the oxygen. So the oxygen gets all the electrons and it gets none. That's kind of what's going on here. So we can kind of generalize this, that oxidization's the normal number of electrons minus the unbound electrons minus the electrons in bonds, right? And you can look at like CO2. You know, oxygen always has a -2 charge. There's 2 of them. To cancel it out, oxygen will have a +4. And you can think of that as like all of the electrons in the bond being given to the oxygen here. And so you can kind of imagine that carbon normally has 4 around it, but now it's given all of its electrons to its neighbors. So it would be that, that 4 -0 -0, because there's no electrons that are unbound, and the electrons in the bonds are really going to the oxygen. So it's got +4. And this normally has 6. It's got 4 unbound ones, and it looks like another 4 there around here, right? So that gives us that -2 charge. So typically, how we're really using reduction number, redox reactions are what we see. And so we can say like this has a 0, this has a 0, this has -2, this has +1. And what we're basically saying is that there's a change in the electronegativities around these atoms. Like if you were to draw out these hydrogens, the electrons were kind of like split between these two right here. And so they really do split it evenly though. And they're sharing it evenly because they're the same ion, right? Or the same atom. And so they're pulling on it equally. So that's why that oxidization number is typically considered zero for these guys. And then we're saying like, well, ultimately I'm going to have this water and there's got to be some new bonds and they're going to have different sharing of the electrons between those bonds. So we're basically saying what's going on in terms of the electronegativity and the things that are interacting, and oxidization number does that well enough. We don't have to draw anything out, you know. Um, Typically, you don't have to draw out like the molecules for the oxidization numbers. You're just kind of working with those. And so if I have another reaction like this one right here, I've got CH4, O2, forming CO2 and H2. And I've just given the oxidization numbers here. And you can see that the oxygen, it was with hydrogen. So it was it had a fair amount of electrons near it. Now it's with oxygen. So it doesn't have very many electrons that it's interacting with. And so although the oxidization number has told us that it's no longer, it's near something that's a lot more electronegative now, so it's effectively a more positive charge, it's not going to give you like the actual charge felt. It's just assuming like, oh, this is purely ionic and all the electrons are going to hang out with the more electronegative one. What would the charge be, essentially? If you were to look at the formal charge on this carbon, it's zero in both cases. So the formal charge doesn't really change here. In other words, the octets are satisfied. So if we go back, and we'll look back at CH4 and CO2, the although there is a change in the electronegativities that we're interacting with, that doesn't matter. Electronegativity doesn't come into play with formal charge. Everything just gets split evenly. And when you do that with these guys, the carbon is like neutrally charged. So these are typically really challenging problems for oxidization numbers. But if you think about this in terms of that higher up table, they're not too bad. So I just kind of want to highlight them. The more electronegative one is the negative charge. Fluorine's more electronegative, so oxygen has to have a positive charge on it. And you can see this is kind of what's going on here in terms of those charges. Like that fluorine, it's got like 8 things that's interacting with, really, because both those electrons go over to that side, right? And then because you got the 6 and the 2 compared to the 7 that it normally has. And then the oxygen, it's kind of losing those, so it ends up having a positive charge. Same thing with the OCl. You can kind of see how that works out, where the oxygen gets all of the charge, so it becomes the -2 charge, and the Cl becomes +1. Okay, now for formal charge. Formal charge, this basically is saying that the electrons are split evenly. You're sharing the electrons. You're thinking kind of covalently. So you're thinking about compounds. You're going to be drawing out compounds when you're thinking about things covalently. And then the real reason that we use these is to figure out the most stable arrangement. So the oxidization number is more about like, well, what is being reduced or what is being oxidized, what's going on with like electronegativities. This is more of like what has the most even spread of electrons within that one molecule. How could we arrange it to spread out the electrons best, in other words? So if we have like CH4, what you can think about is that the math for these guys is that you've got the number of electrons that you normally have minus the unbound electrons minus 1/2 of the bound electrons. So this is 1/2 times 2, because there's 2 electrons in this bond, right? And so hydrogen is neutrally charged here. That's good. We want to have things neutrally charged with formal charge, because in that sense, there's no like hot spots where there's a lot of negativity or positivity in the molecule, but it's just evenly spread out. Same thing here. Carbon normally has 4. There's 0 free floating. There's 8 electrons in the bonds around it, but we only count half of that, and so it's 4. Okay, so the way that we use this is that we'll compare like different arrangements. Like you could arrange this this molecule like here, but A, it's impossible because hydrogen shouldn't form 2 bonds, and B, also you've got a negative spot and a positive spot, and we don't want to have those if we can evenly spread things out. So this is impossible, this is unstable, therefore we can say that this is much more likely to be what the molecule looks like, so we would draw it that way. In other words, our formal charge tells you what the molecule should look like. So if we look at CO2, this is a little bit clearer. You can see that carbon dioxide, if you split the electrons between the two sides, when you draw it this way, everything has 0 formal charge on it. Carbon normally has 4. It's got half of the 8 electrons that are being in the bonds, so it's 0. Same thing, this carbon, or this oxygen, you can say normally has 6. It's got 4 unbound ones, and then 4 in bonds, but it can only interact with 2. So that's 0. So this is very stable. If you end up arranging this slightly differently, like if you take this double bond and then flip that up there and take those electrons, put that on the oxygen, what ends up happening is that you've got a spot here that has negative charge and a spot here that has positive charge. And, you know, magnets, they're attracted to each other. So if these electrons can go over there, they will. So this is very unstable. And what's even less stable is if you have an even more charge all over the place. Like if we were to take those other electrons and put them on the other electron, this is very, very unstable. So we use formal charge to basically say, how do I spread out electrons? And then that allows me to draw out the molecule. So here are some examples of formal charges and oxidization numbers. So if we look at carbon dioxide, we typically don't draw the molecular structure or the Lewis dot structure or anything. We typically just write the formula, assign the charges kind of like this. And then for a formal charge, you would actually properly draw this out and then do some of that math where you've got like first number plus second number plus third number. So that's typically what you're doing with these types of problems. I have drawn this out to help you kind of see what this would kind of look like in that regard. And then we've got another molecule here. We've got H2CO3. And so if we draw out that molecule, it looks something like this, I believe so. Yeah, that looks correct. So if we were to look at this and we were trying to say what's the like the formal charges on these things, we wouldn't need to draw this out at all. We can just say, oh, oxygen likes to have -2, right? Hydrogen tends to have +1. And then it's -2, that's -6. And then we've got +2, and then we've got that blank, and that should all add up to 0. This is -4, so this is +4. And that should work out. So we can look at our formal charges like that, and it's that easy. Like you don't need to draw out anything, but I am just going to label kind of what's going on here in this regard to help you see this. So like the carbon normally has 4, but it's giving all these electrons to the oxygens that are nearby, right? So you can see that this is 4 -0 -0, which is that +4. And you can also see with this oxygen, it's normally got 6. We've got 4 that are unbound, And then we've got another 4 that are in the bonds. That's at -2. And you could also even look at this like, because you can say that all of these electrons are being given to this oxygen, right? Then this hydrogen, I'm not sure why that has that right there. This hydrogen, that should normally have 1, and then there's 0 unbound and 0 kind of in the bonds that it's getting. So this is +1. So this is just kind of like proving that right there, but this isn't typically drawn. On the flip side, if we're talking about the formal charge, this is going to be something where you actually would draw this out a little bit. And let's look at this a little bit differently. So if we're talking about the formal charge on this, if I've arranged this the way that I have it arranged, I believe that's good now. So now let's look at the formal charges more like when you split these bonds nice and evenly. And same here, these bonds are kind of being split evenly. So one of the electrons goes on one side and the other on the other side. So if we're talking about formal charge right here, this would be the 4 minus 0 for the unbound minus the 1/2 for the number of bonds. There's 1, 2, 3, 4. There's 8 electrons in those bonds. So it's 4. So this is 4 minus 4, which is 0. So that's good, right? We want a formal charge of 0. If we're looking at this guy, we've got normally 6 minus the 4 unbound, and then minus 2 because that's half of 4, right? Because there was 4 electrons being shared in the double bond, it's only feeling 2. Then this oxygen you could say is normally got 6, and then there's 4 unbound, and then you can actually see 1, 2 right there because it only gets 1 of the electrons per bond on these formal charges. So there's 2 there, 0. So this is looking pretty good. Like all of our formal charges are pretty good. Like this is 1. There's no unbound electrons, but it does get to interact with one of these. So you could consider this as like 1/2 times the 2 electrons, or you could just say, oh, there's only 1 that you're really getting to interact with. And so we get a formal charge of 0. So this is pretty good. This is a very stably drawn out structure. So that's kind of like what you would see on a problem when you're doing like the formal charge. So it's very likely with these formal charges that you're going to have these calculations. You do sometimes see the oxidization number done like that, but done like this, but it's much less common because we really use oxidization numbers for a reaction, and we use formal charge more for looking at the arrangement of how things are arranged. Because you could try and like look at different arrangements. You could say, well, maybe I've got a carbon and oxygen and another oxygen, and then there's this oxygen off here, right? And maybe my hydrogen's here, and I don't know, maybe one of my hydrogens is here, and maybe this is, I don't know, maybe a double bond, right? And then this can only have 1 more. So you could arrange this kind of differently. And when you do that, you'll find that the formal charges kind of get, they're not as neat. They're not as nice. So we want to arrange in a way that makes our formal charges nice and neat in a sense. I think what ends up being an issue is, I think it's this oxygen right here because it's 1, 2, 3, 4, 5. Yeah, see, this is only got 5 electrons at once to have 6, so it's got like a positive charge, and yeah, it gets kind of messy, right? So you can kind of see that The formal charge, it's more for figuring out how to arrange things within a molecule. And oxidization number is more like working with a reaction. Um, One thing that's worth noting, just briefly, is that resonance also kind of comes into play here. So like this structure right here is a resonant structure. Like it is very stable. If you look at the formal charges on this thing, they're all 0. But you can also have essentially the same molecule, but slightly different, like where you have the double bond on this guy right here. And this is a single bond. So these are equally stable. These are both stable. And you end up having oftentimes these formal charges and resonance. You'll have a number of the polyatomic ions. They'll get stabilized, and this electron can get shared between all those different versions. And in reality, you end up having something that's between a double and a single bond, but you can't really do a formal charge for this thing because you can see it's there's a couple different versions that we're kind of drawing here. But if you were to actually look at the molecule, the length of these bonds are somewhere between a single and a double bond. So this is reality, but can't do the formal charge for that. So it's just something that's worth mentioning. Formal charges help us know what's the most stable version. If you have multiple stable versions, it's probably because there's some resonance like this where the electrons are moving around and they're able to be switched between the atoms. And it's just like a different version of an oxygen or something. So just keep that in mind when you're doing those types of problems. If we're doing like SO4, this is the oxidization numbers. Like you'll see something like this, like +6 and -2. So let's actually do that as that baby blue. And you can see like, oh, these each have -2. It's -8 total, but the total charge is -2, so we need +6 here, right? You could also do the same thing with our CO, this guy right here, because we've got -2 on each one of these, so that's -6, so this is +4 on that oxidization number, right? Because you can say that this, if you were to consider it completely electronically, it's got no electrons and it had 4, so it's lost 4. But if you were to consider it covalently, it's got a formal charge of 0 because it starts off with 4. There's 8 bonds and it's getting half the electrons in each of those. So it gets 4 electrons. So they cancel out, right? So that's just another way of thinking about that. And then, so this is kind of what you would do for like the oxidization number for this thing. Sulfur is kind of weird because you typically only see 4 bonds, but I believe sulfur is the one where you can actually form more than 4 because it's got the d orbitals that it can use in its outermost shell. So you can look at the formal charges on this guy as well, and I believe that this is a net charge of -2. And so if we're looking at the formal charge here for this guy, it would be, it normally has 6. It looks like we have already 6 on there, right? And then there's 2 in the bond, but we're only getting to interact with half of those 2. So we're only getting to interact with 1. So this is a formal charge of -1. So this has a -1 charge on it right here. And I believe this also has a -1 charge on it. And then I'm just curious about the sulfur and the oxygen, what those formal charges are. So this sulfur, I believe, normally has 6. I need to double check that though. Yes, sulfur normally has 6. And then it looks like there's 0 unbound ones, but then we're getting 1/2 of, there's a lot of these. 1, 2, 3, 4, 5, 6. There's 6 of those, right? Um, let's see. Did I do that right? I did not do that right. There's 12 electrons in the bonds. There's 6 bonds. But these should cancel out and give you like 0. Yeah, the sulfur's formal charge here is 0, and I believe this is 0 as well. So oxygen normally has 6. It's got -4, and then -1/2 of 4 here, because it's only feeling 2 of those 4 electrons. That is also 0. So yeah, this molecule, when you've drawn it out that way, these two oxygens have a formal charge of 0. Sulfur has a formal charge of 0, and then these oxygens have the -1 charge, which kind of makes sense because you want the -1 charge on the electronegative atom. It's the more negative something is, the more likely it's going to have the electrons on it in the molecule, right? So you could look at that and you could compare that formal charge to like the same thing but slightly different. So it might be something like this. So instead of double bonds, now you've got a single bond here. And something like this. And in this case, now we've got a -1 charge here, a -1 charge there, -1 charge here, but you also have a +1 charge on the sulfur. So if you were to look at this, we have one less electron that we're seeing here, so this becomes positive, and we've got one more electron over here, so this becomes negative. And so this is unstable when compared to this, which is much more stable due to the FCs equaling 0, or the negative is on electronegative atom. So that's kind of what's going on there with those guys. If you're seeing a reaction, you're most likely working with oxidization numbers and it's a redox reaction. If you're trying to determine the arrangement of a molecule, then you've got to be thinking covalently and be cutting the number of electrons in half in the bond, and that's what the charge is that it's experienced for the math, okay? Or what it is experiencing for the math of calculating the formal charge. So when you see a problem like this, they're asking for the formal charge and they're asking for like this structure. So I'm knowing that we're talking about some sort of like compound, and I just immediately I'm thinking covalent. So I'm splitting those electrons for calculating these formal charges. And I'm going to have to do this with N2O. So I know that that we typically will see opposite charges kind of like bonded to each other. So I'm thinking that we're going to have this oxygen in the center, and then we're going to have 2 nitrogens next to it. And then we're going to have different numbers of electrons kind of like around these things, right? So I want to say maybe something like that. I'm not exactly sure. So the electrons, we can count out the number that the electrons are being contributed by these two things, and we can double check that. There's, it wasn't something that we were doing on the other ones, but something that we could easily do. I think that this is actually good because this is contributing 6, and these contribute 5 each, don't they? For the nitrogen, yeah, they each contribute 5. So this is contributing 6, and then this is 5 plus 5 for a total of, what is that, 16 electrons. And I believe we have that, right? We've got 6 and 6, that's 12, 13, 14, 15, 16. Yeah. Okay, so that's the right total number of electrons. I believe that this is actually drawn out nicely so that if you look here, the formal charges are 0, I believe, because this normally has 6 electrons. There's 4 that are unbound, and then we're subtracting 1/2 times the electrons in the bonds. 1, 2, 3, 4, because it's only really feeling 2, right? So this is 6 minus 4, which is 2, minus another 2, so that's 0. And then we're talking about this guy right here. This formal charge is going to be, they're contributing normally 5. They have 4 unbound, and then 1/2 times 2, which is 1, because it's only really interacting with one of the 2 electrons. So that is correct. That is 0. So I believe that this is the most stable one when you draw it out like that. But let's look at some other possible arrangements. Let's say we've got, I'm thinking that we're going to need to have like double bonds on this, is what I'm thinking. Like if I had these electrons and I scooted them down over here, then that could kind of work, right? I think that, yeah, this still has 1, 2, 3, 4. 4 orbitals are still being used by oxygen. Nitrogen's still using 1, 2, 3, 4. So they're using all of their sp orbitals. They're hybridized, and that seems to be working out pretty nicely. So yeah, we can go ahead and look at these formal charges. In this one, this thing's formal charge was also 0, because it was just the exact same thing as that one. So if we look here, this nitrogen normally has 5. It's got 4 that are free floating, and then half of 4 is another 2. So this is -1. So we've got a -1 charge here. And then I bet this is a +1 then. I'm just gonna say a +1. I can almost guarantee it. So we've got 6, and then there's 2 unbound, and then there's 1, 2, 3, 4, 5, 6. 6 there around there, but it's 1/2 of that 6. So that's another 3. So 2 and 3, 6 minus 5. So this is +1. Yep. Okay. And then this, I think, is still 0, because we have 5 minus the 4 that are unbound, minus the 1/2 of the 2 in that bond, and that equals 0. Okay, so we've got that formal charge there. And then I believe that the third one is I think it's going to be, trying to think, like if I ended up putting this on there, that's going to mess up our there's too many electrons around that oxygen. It doesn't have that many orbitals. So I think what they're going for in this problem would be that now we're double bonded over here. And it's the same sort of idea as this last one, but the mirror image. And so this oxygen is +1 for its formal charge. This is -1, and this is 0. So yeah, these kind of work. The electrons are getting a little bit crowded around other electrons, right? And they're using a lot of orbitals as well. They're all kind of next to each other. So I think that what we want is that original compound with the single bonds. That's the most stable version. And so, yeah, that should be the 3 different versions, and it was this one that was the most stable. And it was due to the formal charges being 0. Like that last problem, we're going to do another one where we need to draw out the molecule. So let's say we're drawing out HCN. You're going to be using the formal charge because we're trying to distribute the electrons evenly and get formal charges of about 0. Ideally, that's what we're trying to do. If you look at these, hydrogen contributes 1 electron, carbon 4, nitrogen 5, so there should be 10 total. And there was a couple arrangements that kind of come to mind when you do that. And I think there's maybe like there's maybe a few more, but there's this one kind of comes to mind. Same with those ones. The question is which one of these is actually what the chemical looks like, which one's the most stable, and that has to do with looking at, well, which one's distributing the electrons the best, keeping them by the electronegative things, but also kind of evenly distributing them. So if we're looking at our formal charges on this, what you can say is that, the carbon right here, it's only really interacting with 2. So it normally has 4. There's 0 unbound electrons, and then there's 1/2 of 4, because there's 4 in these bonds, but we're only interacting with 2. So carbon right here is +2. It's actually a pretty large positive charge. So that immediately, I'm pretty sure this is not it, right? If we look at the nitrogen here, it normally has 5. It's experiencing 6, and then 1/2 of 2. So yeah, this is what, -2? And then I think this is of 1 minus 0 minus 1/2 of 2, which is 0. So yeah, this is that formal charge for carbon, formal charge for nitrogen. So this is not very stable. This guy right here, though, if you were to think about this, is actually going to be a lot better. So like the carbon is splitting these in half, right? Like this nitrogen is got way too many electrons. And also the carbon has not satisfied its octet rule. It's only got 1, 2 orbitals that are being used out of the 4 that it could be using. Empty orbitals. So that's definitely no good. This, on the other hand, I'm pretty sure does satisfy our numbers pretty nicely. So if we look at our formal charge here, this is 1 minus 1/2 of 2, which is 0. Carbon normally has 4. There's 0 unbound electrons. And it looks like we've got 1, 2, 3, 4, 5, 6, 7, 8. 1/2 of 8. We're only really interacting with 4 of them. So it's 4 minus 4. So its formal charge is 0. So this is looking pretty good. And then this guy normally has 5. There's 2 unbound electrons right there. And then it gets to feel half of the ones in these bonds. There's 6 of them in the bonds, so it's really interacting with 3. So this formal charge is also 0. So this looks pretty good. And we have the triple bond between the nitrogen and the carbon. Now this guy was actually the first one that I drew. The reason it doesn't work is because there's empty orbitals. In that center atom. That's really, really bad. Like, you want to satisfy that center atom's orbitals if you can. And we can, and as we saw with the last one. So if we did our formal charge on these guys, that's 0. This is 4 minus 2, and then minus 1/2 of 2. And so this ends up being, what is that? +1, I think, right? And then this is 5 minus 4 minus, this actually might have the wrong number of electrons on here even. Because this is 1, 2, 3, 4, 5. Yeah, it's interacting with 5 because that's 1/2, 2. So this is actually equal to 0. So it's kind of like, where did that charge come from? Unless there was, yeah, there's something that's like missing on here, I think. Actually, I made a small error here. It looks like this should be 4 because this carbon is interacting with 1 and 2, right? So this is actually going to be 0. Okay, so the formal charge is satisfied in this case, but the orbitals are not. So there's a problem there. Um, and if we look at this last case here, we're going to also run into some issues. So that one was not stable because there's an empty orbital. But this one right here, we're looking here, the formal charge is 0. This carbon, again, has empty orbital. So that immediately is like, that's not going to work, right? You should just see that immediately. If we want to look at the formal charge, though, this is 4 minus 0 minus 1/2 of 6. So we end up getting, what is that, plus 1? And then I believe that this would be the minus 1 because it's the 5 minus the 4 minus the 1/2 of 4. Because there's 4 electrons in here, we're only interacting with 2. So this is that minus 1. And so this is empty orbitals and it has non-zero formal charges. So this is very unstable. This is very unlikely to be present. This, you know, has an empty orbital, so it's pretty unlikely to be present as well. This one is the most likely stable arrangement, so most of the chemicals will be arranged like that. This, you could say, maybe some of them, but again, empty orbital, so there's a problem there as well, right? So be careful with those guys. Same thing if we have I and then F3. The best way to draw this, I'm just going to show the stable way of doing this. This looks to me like probably we're going to have another electron pair in there because then that's 4 orbitals. So there's how much are these contributing electron-wise? Iodine normally wants 7, and then fluorine, there's actually 3 of these, so there's 3 times those 7 as well, right? And so I think what we end up getting is 28. It's a lot of electrons. 1, 2, 3, 4, 5, 6. I wonder if that works. Oh, one way that I like to do this is I just think about how much they're contributing. Like this is contributing 6 plus another 1, so it's kind of getting split in the middle there. So if this contributes 1 each, that should be good. So this is 1, 2, 3, 4, 5. So that's only 5. We need 2 more. And then if you think about this, like this electron came from there, this electron came from there, so on and so forth. And that should have it split nice and even. I think iodine is, yeah, it's pretty low down, so this can have more than 4 bonds. So this is okay having the 5 orbitals being used right there. So let's just also double check. We've got 6, 6, 6. That's what, 18. And then another 6. 24. And then another 4, 28. Yeah. So this has the right total number of electrons. Now we can go about actually looking at some of these formal charges. So fluorine normally has 7. We have 6 unbound, and then you've got 1/2 times 2. So I believe that is, that's 1, 7. 7 minus 7 is 0. And that's the case for all of these. If you look at them, they're all 0, kind of like that. It's the same calculation. This iodine, though, is going to normally contribute 7. It's got then 4 unbound electrons, and then 1, 2, 3, 4, 5, 6, and we're only interacting with half of those. So that's 3. So 4 and 3, that's 7. 7 minus 7 is 0. So that's our most stable thing. And if you tried to double bond this, then this is going to have too many electrons for the number of orbitals. Because fluorine, it hybridizes to like sp3, so it's only got 4 orbitals to work with. So you can't really make a double bond by pushing these on there without breaking that octet rule for that. So this is the most stable one. That's how you would draw that out. Typically, when you're working with oxidization numbers, you don't even need to draw anything out. It's as simple as going through and just labeling the parts, like um, 0 and 0, and then this is -2 and +1. And you can think about this in terms of like the hydrogen, where these electrons are being split between the two. And so each one is getting to feel them. And so it's more of like a covalent, or splitting actually evenly. So if you were to keep account of this, this would be 1 minus 0 unbound, minus the 1, or you could say 1/2 of 2 there. And so that ends up being that formal charge of 0. So we can look at these things and draw them out. But typically what we do is we say like the hydrogen, like we can talk about the reactants and the products. So the H used to be 0, and then it was going to the products. And the H was +1, right? And then you can do the same thing with oxygen. Oxygen used to be a 0, and now it's a -2. And so then these problems typically are just like a matter of identifying which one is reducing, which one's oxidizing. You do have to combine half reactions as well. So you're going to need to be able to identify what is changing its the electronegativity based on, or its charge based on the electronegativity of what's around it, right? So this problem right here, oxygen is, looks like it's lowering its charge, so it's gaining electrons. So the oxygen is reduced, and the hydrogen is oxidized, because the loss of electrons, that's an increase in charge. So it's effectively feeling a loss of electrons, because the electrons are getting taken more by the oxygen than they were by the other hydrogen atom. Like if you consider that way, it's like, okay, it definitely has decreased in charge. Now it hasn't gone down a full like 2 charges down, because it is holding on to it somewhat in that bond, but we are able to indicate the change of the charge. Like, oh, this is getting more negative, or this is getting more positive, based off of those assumptions that we usually use. That's typically what you do oxidation numbers with. You typically don't even draw anything out. You're just using those rules that are essentially a shorthand way of doing what I was doing earlier, when I was drawing them out and kind of cutting off the bonds completely when I was doing the formal charge in blue earlier. Those rules just are shorthand for what I was doing there, essentially. All right, well, that's everything for me. Thank you for joining me. I'll see you next time. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking, so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.